Imagine an environment flooded with a constant, chaotic ocean of sound. If you place a completely empty glass tube into that noise, it acts as a highly selective barrier. Most of the acoustic frequencies entering the tube simply bounce around and quickly cancel themselves out, leaving the interior entirely silent. But then, one specific ripple of sound hits the entrance, and instead of fading, it locks into place. This is the pipe accepting that exact pitch. The incoming sound aligns flawlessly with its own reflections inside the glass, building a steady, continuous pattern we call a standing wave. So, how does a simple, empty cylinder decide which pitches get to survive and which ones are destroyed? Resonance, the ability of an object to ring out with a clear note, is a strict filtering process. The rules of that filter are written entirely by the physical boundaries of the container itself. To see those boundary rules in action, let's look inside a pipe left completely open at both ends. This is a schematic of an open pipe. At the open exits, the air particles have maximum freedom to move back and forth. In the physics of sound, these areas of maximum vibration are called antinodes. The simplest, longest wave you can fit inside this space is one that stretches exactly from an antinode at the left exit to an antinode at the right exit. This baseline pitch is the pipe's fundamental frequency. The tube can also accommodate higher pitches, which have shorter wavelengths. The single mathematical requirement is that the wave must always hit maximum vibration at both of those open doors. Because the math works out perfectly for exact halves, thirds, and quarters of that original wave, an open pipe generates a complete sequence of overtones. You get the first, second, third, and fourth harmonics in a clean mathematical ladder. Without any physical barriers blocking the air, an open tube is capable of producing a full, unbroken spectrum of musical notes. Now, watch what happens to the math when we seal one end of that exact same tube. By adding a solid cap, we force a new physical rule onto the system. The air particles trapped against that rigid wall cannot move at all. A point of zero displacement like this is called a node. To form a standing wave now, the pattern has to start at absolute stillness on the left and grow to maximum movement at the open exit on the right. Fitting a wave between a perfectly still wall and an open door means only very specific fractions of a wavelength can survive the trip back and forth. As a result, the closed pipe physically cannot play any of the even-numbered overtones. The second and fourth harmonics are completely skipped, forcing the sequence to jump directly from the first to the third to the fifth. By capping a single exit, the acoustic identity of the instrument shifts, restricting its voice strictly to odd-numbered mathematical patterns. Let's put this boundary logic to a physical test. Take a standard tuning fork. When struck, the metal prongs vibrate exactly 1,100 times per second, producing a 1.1 kHz tone. If we bring that humming fork right next to an open pipe that is exactly 30 centimeters long, we introduce that specific frequency to the air inside. For a 30-centimeter tube with two open ends, the math dictates that its second harmonic sits precisely at 1.1 kHz. The incoming wave fits perfectly. Because the dimensions align, the pipe readily accepts the wave. The air inside begins to oscillate in sync, creating a powerful resonance that amplifies that quiet hum into a bright, loud note. At this exact frequency, the sound is no longer just passing through the air. It is being captured and reinforced by the pipe's own physical limits. The geometry itself has chosen which note to amplify. But watch what happens to that resonant note if we suddenly drop a solid cap onto the bottom exit. The loud hum is instantly shattered. The tube goes completely dead quiet, even though the tuning fork is still vibrating right next to it. Remember, that 1.1 kHz pitch was acting as the pipe's second harmonic, an exactly even number. And a tube closed at one end strictly forbids even-numbered harmonics. The mathematical shape of that specific wave requires movement at both ends, meaning it physically cannot hit a zero-motion node at our newly capped wall. Because the wave no longer fits the boundaries, its own reflections bounce back entirely out of sync. The colliding sound waves cancel each other out through destructive interference. A physical tube does not blindly amplify sound. It acts as an acoustic gatekeeper, singing only when the waves of the outside world perfectly obey the absolute geometry of its boundaries.